Good day, students. Today, let us look into fiber optics and, in particular, the dispersion that occurs to light pulses in optical fibers and application of optical fibers as sensors. Now, in optical fiber communication, information to be sent is first coded as light pulses. Then, light pulses are transmitted from the transmitter to receiver through optical fibers. So here we have an analog signal. Okay. Now this signal is first sampled. We take its values at finite intervals of time, and at these intervals we find its binary equivalent. And thus we have sampled this analog signal into the digital form, and here the binary values are then taken down, and corresponding to these values, light pulses are generated using LEDs. So for zeros, we have light off, then light on, off, on, off, light pulses. Okay. Now these pulses are then given to an optical fiber. The fiber then transmits these pulses, and at the end of the fiber, we detect these pulses using photodetectors. Now the photodetectors will see light pulses as such, on, off stages. Now that is converted into its digital value, and we get a curve like this, and we get an envelope of this signal to produce the analog signal. This is how information is communicated using optical fibers. When light pulse propagates along the fiber, it will broaden. And the phenomenon of broadening of light pulse in time with respect to the input light pulse is known as pulse dispersion. So at the input, if we have a pulse like this, over time, as the light passes through the optical fiber, if it passes through 1 kilometers, so with distance, it will broaden. So if we have a signal 1, 0, 1, represented as light on, off, on, after transmitting over 1 kilometer through the fiber, it will spread, and here, due to the spreading, we won't be able to understand the 0 bit in it. So when these adjacent pulses overlap, the detector will not distinguish between the individual pulses. The dispersion of the fiber will depend on its length. If it has a dispersion value for 1 kilometer, for 10 kilometers it will be 10 times greater. And this dispersion is measured in units of time per unit length of that fiber. Now there are three types of pulse dispersions. The first one is intermodal dispersion. When a number of modes are propagating in that fiber, for example, multimode fiber, the different mode will take different paths, and each of that wave will have different time to propagate through the given length of the fiber. That is, different waves travel with different velocities with respect to the fiber axis. Now, if we have light entering into the optical fiber, and in that light we have different modes. A single pulse can have different modes. Each mode will travel with different velocity, and hence all the different modes will take different paths. Now that mode traveling through the axis of the fiber will have the shortest path, whereas this mode will have the longest path. At the output, the different modes in a light pulse arrive at different times, leading to pulse broadening. The next type of dispersion is intramodal dispersion, also called as material dispersion. Now, a given light source emits over a range of wavelengths. So if I have a light source at 550 nanometer green light, it will contain wavelengths from 500 nanometers to 600 nanometers, most probably. Okay, it need not be very narrow. So when this light pulse passes through the fiber, due to the intrinsic property of that material of the fiber, different wavelengths take different types to propagate along the path. So here, the wavelength of 520 nanometer will have a particular velocity, and the wavelength of 580 nanometer will have another velocity. So in a single light pulse, the different wavelengths will then travel with different velocities. Shorter wavelength travels slower than longer wavelength waves, and hence this causes broadening of narrow light pulses as they travel along the fiber. This is present in both single and multimode fibers. So if we have a light source of lambda 1, lambda 2, lambda 3 width in wavelength, or let us take if we have white light source, it has Waveguide components in it, right? So as it enters the optical fiber, it will separate into different wavelengths, and each wavelength will travel with different velocities. So here, when the violet ray and the red ray contained in that white light pulse is propagated at the same time through this optical fiber, it will take different paths and emerge at different times at the output of the fiber. Okay. This dispersion is called intramodal dispersion or material dispersion or chromatic dispersion. Now the next type of dispersion is waveguide dispersion. Here, dispersion is caused by the different refractive indices of the core and cladding. Now, longer wavelengths have greater penetration into the cladding. Okay, so here, if I have a single pulse in a mode, it may have wavelengths from blue to red. I'm just assuming a blue representing the shorter wavelength, red representing the longer wavelength. The longer wavelength will be penetrating greater into that cladding. Hence, greater portion of the light is carried by the cladding, and in the cladding, the phase velocity of the wave is higher. So this wavelength will propagate faster than the lower wavelength wave. Even though both are in the same mode, the longer wavelength will thus be propagating faster due to the difference in the refractive index of core and cladding. Hence, dispersion is caused by the guiding property of the optical fiber, and it is called waveguide dispersion. Optical fibers with low numerical aperture and narrow spectral width are used to reduce waveguide dispersion. Now, this graph represents the dispersion curve in a material. So we have taken glass, and in that the values of material dispersion is plotted and we get this curve, and values of waveguide dispersion is plotted, it is this curve. And the contribution due to both will produce the resultant along this line. Okay. So from here we understand that the dispersion becomes 0 for the wavelength around 1300 nanometers. Hence, for communication, for light pulse propagation, we use light around this wavelength to propagate through glass optical fibers. Now, optical fibers has a great application as sensors because optical fibers are capable of sensing various physical parameters. And the fibers that can sense and generate information from that are called optical fiber sensors. Using them, we can measure the pressure at a particular point, temperature, electric current, rotation, strain, chemical and biological parameters. Now, sensors can be broadly classified into two: intrinsic optical fiber sensors and extrinsic optical fiber sensors. In intrinsic optical fiber sensors, the parameter to be sensed directly alters the properties of the optical fiber. This in turn changes the intensity or polarization or phase of the light beam propagating through it. So here, at a particular point of study, we may have the temperature changing or the pressure changing at that point. Now, at this point, the physical property of that fiber will change. Okay, it will experience a strain or a pressure or a change in refractive index. And because of that, the light pulse propagating through it will also change in its intensity or polarization or phase. Now for an optical fiber thermometer, when it comes to contact with heat, the temperature change causes change in refractive index of the fiber at that particular point. And this produces a change in the intensity of light pulse passed through it. So using that, temperatures from 80 degrees centigrade to 700 degrees centigrade can be measured. Now, in extrinsic sensors, the optical fiber only acts as a device to transmit and collect light from another sensing element. Okay, so here optical fiber is just giving light to the sensor and it then just collects light from this sensor. Now this is the image of a liquid level sensor, and here we have an optical fiber transmitting light towards a small glass prism. Light is transmitted to this glass prism. Here light gets total internally reflected, and hence the reflected light is captured by the receiving fiber, and light from this receiving fiber falls on a detector to detect it. Now when the sensor is placed in liquid or liquid comes in contact with the sensor, the critical angle at this point at the prism liquid interface is reduced, and this light does not get total internally reflected, it gets transmitted into the liquid, and hence we do not get any reflection into this receiving fiber. So the detector here will not see any light, and hence this indicates that the level has touched the sensor. The liquid level has touched the sensor. Now this type of sensor is used to monitor the filling of petroleum tanks. Optical fibers have been widely used. It has different applications and its use is becoming popular day by day. This is because it has several advantages over other sensors. Its cost is very low and even its size is also very small. The information that we need to get from these optical fibers are very accurate. Also, these fibers have greater flexibility and they are more reliable. They can be used for multiple purposes. And the optical fibers being immune to external interferences, it will not affect the readings that we take from it. So in this session, we have seen what are the different types of dispersion effects in an optical fiber and the applications of the optical fiber as sensors. That's all for today's session. Thank you.